Log on, tune in, find out. Another good idea from Cambridge.
Today is Professor Peter Clarkson from Canterbury. He speaks on vortices and polynomials.
Thank you. I'd like to thank the organisers for this opportunity to participate in this programme. What I'm going to speak about today is mainly results mainly in this paper here that is in applied math. What motivated this piece of work was a figure that I saw in a paper in 2007 by Hassan Aref, who actually the title of the paper is the same as what the title of this talk, Vortices and Polynomials. And he produced this picture of these polynomials, of the roots of polynomials. And I recognized what they were and started to read a bit more, and you'll see where they come from. And one of his motivations of trying to look at these kind of polynomials came from sort of applications of vortices in physics. He showed this is actually taken from a presentation that Hassan Aref gave, where he illustrates vortices in various different contexts: superfluids, plasmas, the Iowa hurricane, a vortex tripole, Bose-Einstein constants, and one that he found numerically, this last picture here. So his motivation is very physical, of trying to find these vortices and find solutions of certain equations in terms of polynomials. So the outline of what I'm going to talk about today is to first show some results that I've been working on in the past few years on polynomials related to rational solutions to the second and fourth Pan-Lavie equations, and with associated polynomials with rational solutions of the KdV and Boussinesq equations, and then show how these results are related to trying to find solutions of this equation, which is the equation of motion for n point vortices with circulations gamma j at positions zj in a background flow. And the connection between the two sets of problems is to find polynomial solutions of this bilinear equation here, where mu and kappa are arbitrary constants. That's the motivation of what I'm going to talk about. So firstly, let's start with Pan-Lavie 2. It's well known that it has rational solutions if and only if the alpha is an integer. And what you can do is, one simple way of deriving the rational solutions is to consider the polynomial defined by this expansion here, and then take a Wronskian of the odd ones, and this is known as the Jablonski-Volger polynomial. They actually derived it using a differential difference equation, but their method involving having to work out Q0, Q1, Q2, Q3, whereas this one will work out Qn in one go. And then you take the logarithm derivative of two successive ones, and you get the solution of Pan-Lavie 2. And something that Liz Mansfield and I did a few years ago was to look at the roots of these polynomials, and that's when we found that they had a very surprising to us at the time, regular, symmetric, and a triangular type structure. What I've plotted here are roots of two successive ones. So the one is the red are, say, Qn minus 1, and the blue are Qn. And it increases as n increases. And you can see they maintain this very regular triangular type structure. Now they are not actually triangles, because if you actually look carefully at the values of the roots, they're actually on an arc. They're not actually on a triangle. I mean, they're actually on a straight line. So we found these regular structures, and in fact, I think that one is one of the ones that appears in the figure by Hassan Aref. Now, to relate it to the program, you need to have some difference equations of some form. And the Jablonski-Volga polynomials, they're originally defined using this bilinear differential difference equation. But you can actually also show they satisfy a fourth order nonlinear ODE and a fifth order quadlinear difference equation. And also the fact that the rational solution of parallel A2 here also satisfies an alternative dp1 given here. So the link between what the some solutions of the difference equations actually are. Now, we then extended that to the so-called parallel A2 hierarchy. This is a hierarchy of equations obtained by symmetry reductions of the hierarchy of the modifier called effective hierarchy. And so the first one in the hierarchy is parallel A2, and then you got a fourth order and sixth order, and the general nth term in the hierarchy has rational solutions of this form, the same form of a logarithmic derivative of two successive polynomials. These polynomials can be expressed as Wronskians, whose coefficients involve these hypergeometric functions that are 1 f2n. So that you have to choose the constants in here specifically to get the relevant one you need, but you can actually then get them all. And if you look at the plots of the polynomials, the roots of them, again, are plotted two successive polynomials. And so you start with a septagon, pentagons, septagons, and just the pattern continues on like this. And so you see that you have these very highly symmetric structures for the roots of these polynomials associated with the parallel A2 hierarchy. So now if you look at what happens to the KdV equation, we know it's the best known example of a Salton equation solved by inverse scattering. It has a scaling reduction to give you this third order equation, which we know is equivalent to parallel A2. Here is the invertible transformation to linking the two. And so therefore you can actually get the solutions of this third order equation in terms of the Jablonski-Volga polynomials. Here it's, instead of being a log of the ratio of two, it's just a log of one of them. And so you can actually get rational solutions of KdV direct just by then plugging this back into the symmetry reduction. But actually you don't even need to do that. You can actually generate the rational solutions. You can actually generate them directly. And in fact, this is a result that goes back to Adler and Moser. In fact, they actually got more general rational solutions. If you now define a polynomial phi n, which through this expansion here, where the exponential now has an infinite number of terms, and all the kappas are arbitrary constants, then you look at this polynomial, which again a Wronskian with respect to x of the odd ones, and this is a polynomial of degree a half n plus 1, so it's a triangular number. And then the KdV has this rational solution where you choose the kappa 2 to be 12t. If you choose the other kappas appropriately, then they are just rational solutions of other members of the hierarchy. So the kappas relate to the different flows in the hierarchy. Now these are known as the Adler-Moser polynomials. They're written down in context of the KdV equation in 1977, but they actually appear in a paper by Birchnell and Chowney in 1929. They actually give this determinantal representation. They're not interested in the KdV equation at all. They're interested in looking at solutions of a different problem, which I'll mention later. And these actually turn out to be generalizations of the Jablonski-Volga polynomials. You effectively, for each of the Jablonski-Volga polynomials, you take kappa 2 to be a constant and all the other kappas to be 0. And the other members of the hierarchy, you just choose one of them to be non-zero and everything else to be 0. And I shall show these actually write a description of stationary vortex patterns. So now let's move on to panel of A4. Now it's well known to have rational solutions for two sets of parameters. Now both m and n are integers, and basically what in the ones here in blue are on these blue dots. This is it's an AB plane where A is alpha and B is the square root of minus 2 beta squared, so these parameters. And these in red are quite these red dots are the center of these triangles. The panel of A4 has solutions in terms of Weber-Hermite functions that lie on these straight lines, and where the straight lines cross, then they can reduce to rational solutions as well. So there's two types of rational solutions. Originally they were given by Naomi and Yamada in terms of differential difference equations. Now he's going to express them now in terms of Wronskians, because that's I think a slightly simpler way of doing it. So if you actually define this Wronskian of n successive Hermite polynomials, which I'm going to call a generalized Hermite polynomial, and then you take special choices of them, one where the m and the n, there's just a difference in the m's change, one where the n's change, and one where they both actually change. Then you get three sets of rational solutions of panel of A4. So those are the blue dots on this transparency here. For the red dots, you now you define a function that's effectively just a scaled Hermite polynomial. And then you take a Wronskian, but it's actually almost like a double Wronskian. Because you take, in here you take phi 1, phi 4, so just take every third one, and then the second set of polynomials is phi 2, phi 5, etc. And then again you get these solutions of panel of A4 in terms of logarithmic derivative of two of them, with this factor of minus 2/3 set. Now what we found with the roots of these polynomials is that for the generalized Hermite polynomials, which are given here, there's again two successive ones are plotted. Yeah, they have a rectangular type structure, whereas for the generalized Okamoto polynomials, the structure has a rectangle in the middle with triangles on the outsides. There's two types of them depending on different choice of m and n. So you can actually get all these different kinds of patterns. And one of the important things it turns out to be is that there are three types of solutions here as well. That will actually turn out to be critical, what I'm going to do. So the generalized Hermite and generalized Okamoto polynomials also satisfy bilinear equations. They've had a whole lot of difference equations as well. That each of them has, I think, 8 difference equations they satisfy. But in particular, they satisfy these bilinear equations here. And again, it's critical that there are 3 of them. Now, to relate them to a soliton equation, take my favorite equation, the Boussinesq equation, which you know has a scaling reduction. The 4/3 there is just for convenience, as is the third in here, purely for convenience. Meant I didn't have to rescale things. Then you get a 4th order equation, which I can solve in terms of panel of A4. And again, I can get solutions of this equation in terms of the generalized Hermite and generalized Okamoto polynomial, so you can get rational solutions of panel of the Boussinesq equation. But you actually don't need to do that. You don't need to go through the panel of A4, or if you know these solutions, you can rewrite a more general way of doing it. You can actually get the rational solutions directly. You define 2 sets of polynomials, effectively one phi n in terms of this coefficient here. So this event literally just generates them effectively in terms of Hermite polynomials, but it's one way of actually doing it. And then you define two Wronskians, one analogous to generalized Hermite polynomials, one analogous to generalized Sakamoto polynomials, and then you get these rational solutions of the Boussinesq equation, which you can obtain through the reduction to P4. But the important thing here is that I was then wanting to consider whether I could find more general rational solutions by adding some terms to this exponential akin to what you did for the Adler-Moser polynomial. The Adler-Moser polynomials had an infinite number of terms in here, and basically, can you add an infinite number of terms? Well, it turns out that if you add a lot more terms, it only works in one of the two situations. So here I've added all the extra terms, then only the ones related to the generalized Okamoto polynomials turn out to be actually solutions. If you do the analogous thing to the generalized Hermite polynomial type solution, you find that all the parameters here, all the kappas, have to be put equal to 0. So you get these excisional solutions, but only in this case. However, there are even more solutions, rational solutions of the Boussinesq equation. Here's one given by Aldowitz and Satsuma in 1978. And they obtained it by taking the long wave limit of the two soliton solution. So there are more as well. So how does this relate to vortex dynamics? Well, firstly, if we look at the equation of motion for n vortices with circulations gamma j, positions zj, this is the equations of motion. In this first case, I'm taking the case where there's going to be no background flow at all. Now, if the vortex configuration rotates as a rigid body with angular velocity, then the derivative is quite straightforward. They just look minus I omega zj star, where zj is the complex conjugate. And so you have to solve this system of equations here. Now, if all the zj's are real, then it's actually quite easy to solve the problem. And all the gamma j's are equal, then effectively by rescaling xj if necessary, you have to solve this system of equations, discrete system of equations, note the Stilts's relations, and it's well known that the only solutions to these are the roots of the nth Hermite polynomial. So that if you want to solve the solutions of this are just given by the roots of the nth Hermite polynomial. So if it's real, the problem is straightforward. If zj is complex, there's no analytical formula yet known. People have only found solutions numerically. Anyways. So now I'm going to first consider the case of vortices of the same strength and mixed signs. So you've now got m plus n point vortices. And I'm going to suppose the vortices at Z1 to Zm have strength gamma, which is positive, and the vortices at Zm plus 1 to Zm plus n have strength minus gamma, so you have n negative vortices. And then I'm going to define the polynomials p and q such that the polynomials p have roots at the vortices with positive strength, and q as a polynomial with roots at the vortices of negative strength. And I'm going to first look at two particular cases. One, stationary vortex patterns, which is when this is actually equal to 0. And the other one is just a constant. Now, those are called translating vortex patterns. And both of these you can solve in terms of the Adler-Moser polynomials explicitly. So just to remind you, these are what the Adler-Moser polynomials are. You define the phi n through this exponential and then take a a Wronskian of the odd ones. C is a constant, but it actually plays, we normally choose C so that the Adler-Moser polynomials are monic. These are three of them. See the capitals, and they get increasingly more complicated as you go along. Now they actually do satisfy differential difference equations. These are the two differential difference equations they satisfy, and both of these differential difference equations appear in the paper by Birchnell and Chowdhury in 1929. Now it's an interesting paper. This was published by the London Math Society. It has no references, so we've been not allowed these days because in the one we all have to have lots of citations. And also in the appendix is a rebuttal to the referee. Say the referee was wrong. To explain why the referee was wrong. So what for stationary vortex patterns? So remember that there's a piece of chalk. P is the product of when the positive circulations, and Q is the polynomial where you have, oops, I just mean one to end, where you have the negative circulations. And then what you can show is that necessarily P and Q have to satisfy this bilinear equation. It's quite easy to show that, quite easy calculation to do. And then to link them to the Adler-Moser polynomials, if you take P and Q to be two successive Adler-Moser polynomials, then what was shown by Birchnell and Chowdhury and later by Adler-Moser was the solution of this equation was just given in terms of the Adler-Moser polynomials like that. Now, one thing to note is also that if you take the Schrödinger equation with the potential, it's the twice the second logarithm derivative of the Adler-Moser polynomial theta n, then the solution of this is just a ratio of these two polynomials. What you can then note is that if you take this Schrödinger equation and you put u equal to minus 2 times the second logarithm derivative of q, and you put psi equal to p over q into here, you just get back equation 1. So you get this link between these, the Schrödinger equation with zero eigenvalue and this bilinear equation here. So stationary vortex patterns was easy. Translating vortex patterns is almost as easy. Now in translating vortex patterns, you now have a case where you now just have this additional term added on, where mu is a constant related to this the constant velocity. And now you take the Adler-Moser polynomial, then you take what effectively is a modified Adler-Moser polynomial. You take the same phi's that I had before, and on the last column you just add of the Wronskian, you put e to the mu z. Then you have to put an e to the mu z out the front to generate a polynomial. And then you get these, the solution of equation 2 is that q is the Adler-Moser polynomial, and p is just this modified Adler-Moser polynomial. And this is another way of actually trying to generate or show the relationship between the theta n and the theta n tilde. So it really just is a modification of it. And effectively what Ted Adler-Moser showed, if you now take the Schrödinger equation, now you have a non-zero eigenvalue, and you take the potential that's the minus 2 times the second log derivative of an Adler-Moser polynomial, then this has solution where it's the ratio of the modified Adler-Moser polynomial and the Adler-Moser. And again, you can show the link between this Schrodinger equation and the relative bilinear equation. This is the relationship between them. So show an explicit link between these two types of solution. So now I want to move on to what's called quadrupole background flow. So I now have same situation before, but now I just add on this additional term. And so now what we're going to do is take the almost the simplest case. I'm going to suppose there's the stationary, and I take this W to be effectively linear. And then you have M with positive flow, N with negative flow. So you take again these polynomials here, and then it can be shown that using these relations here, that P and Q now satisfy this bilinear equation here. It's not a particularly difficult calculation to do. You just have to keep differentiating and then using these relations here to work out what's actually happening. And what you do note from this equation here is that if Q is 1 and mu is minus 1, then P satisfies the equation for the mth Hermite polynomial. Now what you should note here as well is on the right hand side you've got M and N. M is the degree of Q P, and N is the degree of Q. That is quite important. That factor does have to be M minus N to create a balance. So, Gansky and Campbell actually tried to find some polynomial solutions of this, but they claimed that there weren't any for M equals N equals 6. They were using computer algebra in the 1980s, though. However, using computer algebra 20 years later, weren't able to find them. Here are some for M equals M and N, both the same, 2, 3, 4, and 5. And there are some for M equals N equals 6 and M equals N equals 8. One was able to just quite easily guess the form of the solution, put it in, get Maple to solve for the coefficients, and you find out all those solutions there. So you can actually find them. I could also find them when M equals N plus 1. So here are some where the degree of P is 1 more than the degree of Q, and again we can actually find a whole lot of solutions. And these are some of the plots for M equals N equals 6. They're quite structured. These are, again, there's both P and Q in there, and I've forgotten which is P and which is Q, whether the red is P or the Q is, whether they're both on there. And again, for M and N equals 8, they've all a certain amount of symmetry. And if you then start to look at M equals 7 and N equals 6, this one here is, well, the two solutions are just effectively the two Hermite polynomials, actually. And again, you get different kind of patterns as you go through. Then if you look at this bilinear equation, remember that my generalized Hermite and generalized Okamoto polynomials also satisfied bilinear equations. You can find they actually have that exact form here. For generalized Hermite, you have to have mu equals 1. For generalized Okamoto, you have to have mu equals minus a third. And again, there are 3 sets of these solutions, and here are they written down what they actually are. So I could find the solutions there. And then I wanted to try and relate this to a Schrodinger operator to try and find out some more information of what we get the general form of the solution. So what is the form of the solution of this bilinear equation? So firstly, if we take this Schrodinger operator, then it is said to have trivial monodromy if all the solutions of the corresponding Schrodinger equation are meromorphic in C for all lambda. And then that operator is said to be monodromy free. And Duistermatter and Grunbaum consider the classification of Schrodinger operators for rational potentials which decay to infinity, and they got this result that if the U had to decay to infinity, it had to take this particular form, whereas the new J are integers, And you can have these poles at these ZJs. These are the only operators with decaying potentials where had trivial monodromy. Then Oblomkov generalized this result to rational potentials which had a quadratic growth at infinity. So now you can have a z squared here as well, and then the r has to go to 0. And they found that the operator had to be that it involves this logarithmic derivative of the Wronskian of L Hermite polynomials, but they have to be distinct integers, so these have a distinct sequence of integers. So they found that this was the result that was proved 10 years ago. And then using effectively correlative results of Crumb's 1955 paper, effectively he set this almost like an exercise. But, if you take the Schrödinger operator with this potential, so that's the potential that Oblomkov actually had, then the solutions are come in two forms. You either add on one more Hermite polynomial, and you've got an exponential function as well, or you take one off. So you can, and you see the relationship between the Schrödinger operator and the bilinear equation I'm interested in is if you let u equal z squared minus 2 times the second logarithm of q, and psi equal to p over q times the exponential, then this links these two equations. So there's a distinct link between a Schrödinger type problem. And then consequently, you have this result that was actually explicitly written down by Luzhenko in 2003, which says that this bilinear equation has these polynomial solutions where you take p and q, and p has a Wronskian which involves one more Hermite polynomial than the one for q, and there's a distinct sequence. Now, the thing to note about the polynomials here is they don't involve any arbitrary parameters in contrast to the Adler-Moser polynomials. And so you might think that that's actually it, the problem's solved. This gives all the answers. Then I went and looked at the results of the generalized Hermite and generalized Okamoto polynomials. And I realized that only 2 of the sets of 3 each case satisfied that condition of one Wronskian having one more Hermite polynomial than the other. And so for the generalized Hermite polynomials, you can get solutions that have the same number of Hermite polynomials. One's just, it's got to be a specific sequence, and this is a shifted, but they've both got this. So P and Q now have the same number, whereas in the theorem before they had to differ by 1. And for the generalized Okamoto, then the P has 2 fewer than that for Q. So there's a difference of 2, not 1. But you can actually extend that. You can now define Wronskians in terms of Hermite polynomials. They're rather complicated formulas looking. These for n greater than 2, if n equals 1, it's just the generalized Hermite polynomials. So you just simply keep adding more sequences of the same type of form. The bottom one differ from the top one by a difference of 1. And then you can also do essentially a generalization of an extension of the generalized Okamoto polynomials. Just keep adding more of these as well. So in this one, they have the same number of Hermite polynomials. This one, the P has n fewer. And in fact, both of these sets of polynomials are related to rational solutions of symmetric P4 hierarchy due to Naomi and Yamada. So that for this symmetric system here, these polynomials are related to the rational solutions of that. So you can get all these additional solutions. Then, again, just by trial and error, just by plugging in NANSAT, working out the solution and seeing what actually happens, I found all these other different kinds of solutions. These are solutions when m equals n. These involve linear square roots, and they also have i's, and they certainly can't be expressed as Wronskians of Hermite polynomials. And you can do the same for an m equals n plus 1 as well, I found a whole lot of solutions of this just effectively by plugging in answers and actually solving for them. Now, I want to just briefly mention some results I can do with some other vortex solutions of a complex sine-Gordon equation that I've recently found with my graduate student Bryn Thomas. So if you look at this two-dimensional complex sine-Gordon equation, then if you look for a separable solution in polar coordinates, and this is referred to as a n vortex configuration, then the Qn of R satisfies this ODE, which is solvable in terms of Panlevet 5. In fact, if you let Qn equal 2 over 2 divided 1 minus W, then it is Panlevet 5, because alpha equal to 0, beta equals to minus 2n squared, gamma 0, and delta's 2. So now, and so what you can, and what we'll be able to show, which I'm going to illustrate on the next slide, is that rational solutions of this equation, and also of Panlevet 5, can be expressed in terms of Wronskians involving associated Laguerre polynomials. So we can get at the whole sequence of solutions. Previously, Barashnikov and Panofsky and Enolf and Barashnikov showed there was a sequence of 4 Schlesinger maps to get from Qn to Qn plus 1. So you have to fold these 4 Schlesinger maps at each stage to get it. So it was actually fairly complicated, so that effectively only wrote down about Q1, Q2, and Q3, because it was a fairly laborious situation. But actually what you can do is a quite different kind of thing. I'm now going to set up 2 functions, one of phi k that involves a Laguerre polynomial, but it also has an exponential out the front as well. So it's an associated Laguerre polynomial, and psi k is also an associated Laguerre polynomial. And then you define this double Wronskian, and if I put this factor here, this exponential, it cancels out the fact I've got n of them appear as well. Then I get a polynomial of degree n times n plus 1. And then what you find is that they're making specific choices for this parameter mu that appears in here. This is a solution of this equation here. So I've got these rational solutions of this Qn equation arising from the complex sine-Gordon equation. And so here are 2 of them. So I was interested to see what the roots of these what these solutions were, and this is what Q10 actually has to be. Now we actually had immense difficulty getting this. When we worked out the polynomials, and then Maple just refused to give the roots. It just refused to give the roots at first. And so we tried using MATLAB. But MATLAB does a rounding error. And it gave pictures that were completely wrong. You could do the calculation in about 2 seconds, but gave the wrong answers. But eventually I managed to persuade Maple to give me the roots, and we got these exotic patterns here. Okay. So the conclusion of what I've talked about, looked at some special polynomial associated rational solutions of P2 and P4, and they wrote very symmetric structures, and the same is true of the rational algebraic solutions of P3 and P5. We looked at rational solutions of KdV and Boussinesq, and you can get some generalized rational solutions which involve an infinite number of parameters, but these only exist, or only seem to exist, when the original rational solution is decaying. If it's non-decaying, you can't generalize it. And we've got similar results for nonlinear Schrödinger, dispersive water wave, modified Boussinesq, etc. And it's another property of these integral differential equations, particularly solitone and Panlevet equations. And then I've shown that they've got applications in the description of vortex dynamics, particular shown that there's more solutions of this Schrödinger equation where R decays as Z goes to infinity than had previously been thought. And so some open problems. I'm still wanting an explanation of why you get these pretty computational results. We've not looked at rational solutions or algebraic solutions of P6, or really of discrete Panlevé equations. Now, for some of the difference Panlevé equations, we know that they have solutions in common with the standard Panlevé equations, so therefore we've got some of the polynomial solutions. In particular, a big challenge here is to find what happens to the Q difference equations. We've no idea, do their polynomials have any roots of significance or not? I don't know. Because the Q polynomials seem to be quite different, or the Q discrete Panlevé equations are quite different to the standard D equations. So what can you do with rational solutions or the special solutions of other solitary equations? And do they have particular applications? I mean, I've shown it sort of an illustration within vortex dynamics. Some of the Wronskians that I've had for, certainly for Panlevé 3, Panlevé 4, and Panlevé 5, their rational solutions arise in random matrices. And I don't know what the positions of the roots of those polynomials mean in the random matrix context, or particularly have these got any application in numerical analysis? Well, in classical numerical analysis, special functions are used quite extensively, such as the Chebyshev polynomials. So do these have any applications? Moving on to I've shown some more solutions of this equation. How do I know I've got them all? And the bigger challenge is, I just looked at the case when the vortices had either positive or negative circulation and they were equal and opposite strengths. What happens if they're not equal and opposite? Even if you try to put in, then the polynomials or the bilinear equations have these kind of forms, where mu and kappa are arbitrary constants, and gamma effectively is a ratio of the two strengths of the different vortices. Now, Lutsenko obtained some polynomial solutions of this one when mu equals 0, when lambda's 2, and that corresponds to vortices of two strengths of an equal magnitude. But what more can you do? Are these even related to integrable problems or not? My guess is they're probably not, but I don't know. Thank you.
I have a question about the detail in your story about Boussinesq, actually. You had a case where you said you couldn't add higher order terms in the exponential.
Yep.
Now,
Yeah.
in the next example.
Well, yes. Right. Yeah.
Yeah. So, looking at this exponential between brackets, I would guess that you have to start actually with the next power in lambda with j equals 4.
If you put kappa 3 equal to 0, you meet kappa 4 equal to 0. Kappa 4 equals 0 equals kappa 5.
No, but I think in the Boussinesq case you have to omit the kappa 3.
I have done.
Okay.
I've done that. If I omitted kappa 3, I was forced to have kappa 4 equal to 0. If I omitted kappa 4 and kappa 3, I was forced to have kappa 5 equal to 0.
Why is that?
I don't.
Because you see in the dispersion relation, if you look at the hierarchy for Boussinesq, it is the third of order flow that have to be taken out.
Well, I understand what you're saying, but I've actually tried that.
Okay.
I found necessarily in sequence they all had to be 0.
Okay.
Well, up to about kappa, up to n equals 6, and then I get that.
Except.
I
I
thought
haven't done the computation.
if they're not going to work for the first few, they're not going to work at all. Well, that's right. But this pattern has been true for other solitary equations we've looked at. If you look here, these solutions are not decaying as x goes to infinity. These are. And that just seems to be the defining factor. It's true for nonlinear Schrodinger, it's true for modified Boussinesq if it was a classical Boussinesq system, true for dispositive water wave equation. And in fact, for nonlinear Schrodinger, it's the opposite way around. It's the solutions that come from the generalized Hermite polynomials that can be extended, whereas the ones that come from the generalized Merton polynomials can't be extended. So it just varies as well. The only common thing we seem to find, right, which is only an observation, is you have to have a decaying solution. I don't know why that's true. That's just. I mean, I did think, well, maybe just as that in KDV, you only take the odd ones. But no, you just simply, if you take these, you find that kappa 3 has to be 0. You leave kappa 3 out, kappa 4 has to be 0.
But I agree with Frank. I mean, these are the